Okay, in this video I'm going to continue on with my tutorials on thermodynamics and statistical mechanics. This is video number 46 and we're going to discuss the van der Waals model. So I'd like to draw your attention to my website universityofphysicstutorials.com. This will be one of the first of three videos on the van der Waals model. The previous videos which are relevant to this are are as follows. Number 4, where I discuss the ideal gas law. Number 36, where I discuss the thermodynamic identity. Number 39, where I related the thermodynamic identity to the Gibbs free energy and got the Gibbs thermodynamic identity. And number 44, where I discussed phase transformations. So these 4 videos will be relevant to each of the 3 videos on the van der Waals model. So what is the van der Waals model? Well, it's a mathematical model for liquid-gas systems. That's the first thing. So we're going to come up with some sort of functional form, a mathematical function to analyze liquid-gas systems. But we already know a function which analyzes liquid-gas systems, and that's the ideal gas law. But the ideal gas law isn't perfect. For example, it allows the volume of a particle to go to 0 and doesn't account for intermolecular forces. So for that reason, what the van der Waals model does is it adds 2 correction terms to our ideal gas law, and it becomes our new mathematical model for liquid gas systems. So the 2 correction terms are, as I said a moment ago. The first one accounts for the fact that there is in fact a finite molecular volume, and the second one accounts for the fact that there are intermolecular forces, attractive intermolecular forces. So how does that affect the ideal gas law? Well, because there is a finite molecular volume, we have to increase the volume term in our ideal gas law, and because there are intermolecular forces, attractive intermolecular forces, we need to reduce the pressure term in the ideal gas law. So that's really what we're doing. And what we're going to do is come up with some sort of a mathematical function which will adjust the ideal gas law accordingly. So with those 2 requirements, what we'll find is that the pressure of an ideal gas is going to be less than the pressure of a real gas. Okay, so we're going to have to reduce the ideal gas law term by, it's going to be P real plus another pressure term. So in other words, the pressure of a real gas is less than the pressure of an ideal gas, but the volume of an ideal gas is going to be greater than, we'll say, I'm going to say VA for the adjusted term and PA for the adjusted term. So this is going to be V real. So the volume of an ideal gas is greater than the volume of a real gas. The pressure of an ideal gas is going to be less than the pressure of a real gas. Alright? Sorry, the volume of a real gas is going to be greater than the volume of an ideal gas, and the pressure of a real gas is going to be less than the pressure of an ideal gas. Okay, so where do we go from here? Well, the first one I'm going to talk about is the volume. So I think it's fair to say that each particle is going to have a volume. So we're going to say that the total volume, okay, we'll say is going to be the number of particles n multiplied by the volume per particle b, and this is going to be our correction term. Alright, so that should make sense. So this b is going to be a constant, and this is the total number of particles. So what we're going to do is we're going to add this to our ideal gas, and we're going to get the volume for our real gas, and it's going to be as follows. We're going to have it's going to be V minus NB. So V ideal is going to be V real minus NB. This is the van der Waals adjustment term for volume, because we have a finite volume per particle, so we need to reduce the volume of our ideal gas. We'll say the V ideal is V real minus NB, if you want to look at it that way. Okay, so that's how we get the volume for our real gas. Next, we need to look at the pressure term. So, well, that was the easy term. The volume term is easy. That's why I did it first, of course, right? So we need to look at the pressure term. Now, where do we start? I think the best way to start is as follows. If we look at the thermodynamic identity, du is equal to TdS minus PdV plus mu dn. Now if we talk about infinitesimal steps, we'll say small steps, if we talk about infinitesimal steps, we are able to hold both the entropy and the number of particles constant. Right, so if we do that, we see that the partial derivative del u del v is equal to minus p, or we could say minus del u del v is equal to the pressure. The point here is this: if we get in a potential energy term, because we'll say the reason the pressure of a real gas is less than the pressure of an ideal gas is because there are attractive intermolecular forces, so there's a potential energy. So if we somehow get this potential energy term and we take its partial with respect to volume, we will get the associated pressure term for our ideal gas. So what we really require is this the functional form for the potential energy term associated with these intermolecular forces. Now, we'll say, I'm going to call it U. U should be proportional to the number of particles, or the density, we'll say. It should be proportional to the density. Why? Well, if you double the number of particles, surely you have twice the number of particles attracting any individual one. So the intermolecular forces should go up. Okay? Not necessarily in proportion, but they definitely should go up. So what is the density? Well, that means it's going to be proportional to the number of particles divided by the volume, because that's what the density is. Furthermore, we know that it should also be proportional to the number of particles. That's just common sense. So putting those together, U should be equal to a constant, I'm going to call it A, multiplied by what it's proportional to, n over v and n. So it should be a n squared over v. That is going to be the van der Waals correction term for the potential energy associated with the attractive intermolecular forces. So if we get del u del v, which is equal to minus p, okay, and that's going to be minus a n squared over v squared. That's some pretty straightforward derivatives. So p is going to be equal to a n squared over v squared. Putting it all together, we're going to find, just to remind ourselves, p ideal is p real plus this, we'll say, adjustment term. So we're going to get p ideal is equal to p real plus a n squared over v squared. Alright, now we have our second adjustment term for the van der Waals model, and this one adjusts the pressure, in that it reduces the pressure of an ideal gas to what it should be for a real gas, or, well, closer to what it should be for a real gas. So if we put all those together, we had PV is equal to nKT. This is the ideal gas law. But what we saw now is that we're going to go from V to, so V is being transformed to V minus NB, and P is being transformed to P plus a n squared over V squared. So if you plug both of those in, we get a very straightforward result. We're going to get P plus a n squared over V squared times V minus n times B is equal to nKT. And this is the van der Waals equation of state. The reason it's called an equation of state, of course, is because it relates all the different quantities, and that's what we call an equation of state. It tries to, an equation which tries to relate all of those. Now, just to remember, just to do a small bit of a recap, because I suppose that's really all I want to say, but I suppose that is the result, but it's not all I want to say. If we plot on a pressure-temperature graph, or PT diagram, which we did in a previous video, we saw, for example, let's look at CO2. I think CO2 did something like this. And there came a point here which we called the critical point, the critical point. And the issue here was, let's say we were on one second, I'm going to draw this in green. So what we had is we had the solid phase, the liquid phase, and the gas phase. So let's say we were on the line here I've drawn in green, which is the liquid gas phase line. So we have our substance existing in equilibrium between the liquid and the gas phase. But if I increase the temperature I will now go from liquid to gas. Okay, so I'll start to boil, I suppose. But if I increase the pressure, then I come back onto it and it becomes both a liquid and a gas as well. But as you do that, you're increasing the density. So the difference between, or the difference between your liquid phase and your gas phase is getting less. So as you keep doing this, the difference gets less and less and less. Okay? So what we say is there comes a point where there's actually no distinction between the liquid and gas phase, and we call that the critical point. And this line, this liquid gas phase line, does not extend past the critical point. So we like to plot the critical point because it's very useful. So if we plot our PT diagram, or sorry, this time we're going to plot a volume, V over V critical, and we're going to plot P over P critical. It's not a PT diagram, but rather a PV diagram. That's important because I often forget that myself. So we're going to plot these at constant temperature, so we're going to get an isotherm. And the isotherms start to look something like this. Okay, so you'll see this lower one here is the one that you'll usually see associated with the van der Waals model. So what we're going to get, T critical, of course, is the critical temperature, P critical is critical pressure. So, and I said, when a liquid and gas cease to have a definite boundary due to increased pressure and density, we call that the critical point, or the critical temperature. So this is I suppose the archetypal drawing or diagram when we're talking about the van der Waals model. Okay, and after rubbing out the V. So for this video, that's all I've got to say. Thanks for watching. Please pass it on to your friends, subscribe to my channel, and you might also click on universityphysicstutorials.com.